Hello there to the students taking the Spring 2025 collage seminar on coronal heating and or coronal cooling. I had just a few things I wanted to talk about that I think might be useful moving forward in this course, mostly about some of the quantities, the coronal heating and cooling quantities, rates, fluxes, however we want to talk about them, and also the units of those quantities. Um, for specifically for students who might not be too familiar with this topic, I just wanted to lay out a few basics that I think might be helpful. First, of course, is that infamous equation that we talked about on, I guess, Wednesday, January 22nd, right? This is from Sakurai's paper. Um, I just wanted to allay any fears about this equation. This equation really isn't something strange. It's something that I'm sure you've seen before in other disguises. So I just wanted to talk through it a little bit. The way I think about this equation is essentially as a conservation equation for the thermal energy density of a gas, right? So it's an energy conservation equation, but just for the thermal part, the U TH here on the left-hand side is the thermal energy density. An energy density is, joules per unit volume, and the partial derivative with respect to time is showing how it evolves, right? These and everything on the right-hand side are the sources and sinks, right? Sources of heat and ways that heat can be taken out of the system, right? We're solving this for a parcel of gas or a parcel of plasma, and we want to know how do things heat up and cool down, right? So all these sources and sink terms correspond to the ones that we've seen. We have our radiation term. Oh, by the way, I think that to put them with the same signs as the one up here, I think we would have to take these terms from Sakurai and put them all on the right-hand side, right? Positive terms like the coronal heating term represent sources. The radiation is always negative, so once it's on the right hand side, it'll have a minus sign, and the conduction can be positive or negative depending on the gradient of the temperature. So yeah, we talked about those. There are also these other terms that for the first part of this course I think are going to be unimportant, right? We're going to be dealing with um, a time steady situation, so there's no variations in time. And we're also not going to deal with bulk flows of the gas in any one direction, right? So for the coronal loops, the static, hydrostatic parts of the corona, we don't need to worry about bulk flows. So it's only the radiation conduction and direct heating. I also wanted to say that this is something that I'm sure you've seen before under the name of the first law of thermodynamics, right? When you learn thermodynamics, this first law comes into play. If you want to change a parcel of gas or fluids thermal energy, right, that's the left-hand side, there's only two ways to do it. If it's an isolated parcel, you either supply uh, heat to the parcel, right, that's the coronal heating, or you do work on the parcel, or the parcel does work on its environment, right? The PDV, mechanical energy work done. In the case of if you look at these equations from fluid dynamics, those correspond to non-zero flows, right? Expansion or contraction involves the divergence of the flow field either being positive or negative. But again, we're not going to worry about that. And these other terms, of course, radiation is just a negative heat supplied to the parcel, right? Heat is being removed from the parcel. Conduction involves breaking down the idea that this is a single isolated parcel, right? If you have parcels next to each other, they can conduct heat between them, right? And that's why this thing can be positive or negative, depending on which way it's going. All right. The other thing I wanted to talk about, and I'm replacing that epsilon with a Q here just because I'm more comfortable with Q for these units, is the units. And the units are kind of important. And in Sakurai's paper, he actually provides two different ways of talking about essentially the same thing. So I wanted to make sure that we're on the same page with that too, right? These Q units, I said before that the Q was an energy density per unit time, right? So that's, in CGS units that you'll often see in the solar physics literature, is, ergs per cubic centimeter and then per second. uh, but you can also take the ergs per second, and that's a power, right? So if you wanted to do it in SI units, that power would be watts, or I like kilowatts, as we'll see soon. And then the volume will be meters cubed. So this Q is often called, specifically for the external heating term, it's called a volumetric or a volume-based heating term because it's power, some amount of power is being injected into this parcel per unit volume. The other quantity that we talked about a lot as a vector quantity, or at least as a quantity with sign, is the flux of energy, right? I'm sure you've seen energy flux, right? It's energy per unit area per unit time, or power per unit area. So the way to think about that is that if you have some sort of little piece, little area that energy is flowing through, the flux tells you how much energy is flowing through there through that area per unit time. Another way to think about flux is to take that energy density, right, joules per meter cubed, and multiply it by a speed, meters per second. The meters cancel out, and then you have the second here. So it's how much energy is being transported with a certain velocity. It's another way of thinking about the energy going through an area and being transported somewhere. Of course, these two quantities go together, right? The Q on the right-hand side has the divergence of a flux on the left-hand side. And of course, you can think about them just in terms of units. There's the only big difference is one factor of length, right? You can think of the volumetric rate as the flux divided by another length quantity, or you can think about it as the actual spatial derivative, or the divergence of the vector quantity. Yeah, and I guess again, these things work together, right? If you take a flux of energy flowing through an area and you look at how that energy eventually fills up some volume, right? Think about a cylinder, right? There's an end cap of a certain area, and then there's a length of that cylinder, and together the area end cap times the length represents the volume. So to convert between energy per unit area and energy per unit volume, you just have to divide by that length, right? We're going to be talking about field lines flowing through the corona, so and coronal loops where the field line reaches the sun on both ends. So this L can be thought of as the length of that loop, length of that field line. And Sakurai gives these different numbers, but again, I think they're really the same thing, because at the end of section 4, Sakurai talks about a typical coronal heating rate of 10 to the minus 4 to 10 to the minus 2 ergs per centimeter cubed per second. But that is really the same thing as what he gives in the table earlier as an energy flux of 10 to the 5 to 10 to the 7 ergs per centimeter squared. These things are equal if you're talking about a length that converts the two of order about 10 megameters. And that is a very typical coronal loop length. So yeah, it's really the same thing. And I think it's nice to make sure that we understand how these things convert into one another. The last thing, of course, is to go from these CGS units to the SI units. And the reason I like kilowatts per meter squared for fluxes is because in the corona, these things are of order 1, right? They go from, about a factor of 10 up and down from 1. And if you want to know more about how much energy is actually available for the coronal heating in terms of these kilowatts per meter squared, I can point you to my lectures, which have video recordings and slides that you can look at from the 2022 collage/seminar that was also on coronal heating, but also talked about space weather and other things. But the first few lectures, I think, might also give a nice introduction to coronal heating. And I can point you to the website here. I'll also put the web address in the discussion below. So yeah, I think that was all I had to say, and I look forward to how the rest of the semester will go.